Let us start with considering a system of n identical particles. We are assuming that the particles are independent. There are no forces. The total energy let us emphasize that these are independent. The total energy is a sum of individual particle energies, like E1 plus E2 up to En. Now, in general, the particles could be different types of particles. That means each particle may have a different set of energy levels. So let us indicate some of them. This is for particle 1. Now, if particle 2 is different from particle 1, then its energy levels would be different from those of particle 1. So, this is so in this expression, value of E1 could be any one of these numbers, this one or that one or that one, or any energy level of particle 1. Similarly, E2, this is the contribution from particle 2. This number could be any one of these allowed values for particle 2. Similarly, for the other particles, let us say, etc. Now, when the particles are identical, the allowed energy levels for each particle are the same. So, which means we don't have to write n different energy levels like this, because all of them are identical if the particles are identical. Just one of them is enough, because all particles are identical. Okay, now this is the case we are considering, identical particles. In this case, what we do is we can write this expression in a different way. Let us number or label the energy levels of just one of these identical particles. Call this one E1, this one E2, this one E3, and so on. Please note that the use of integer index to label the energy levels is different from this expression. Here, the index 1, 2, 3 is labeling each particle. However, in this notation here, the index 1, 2, 3 is labeling energy level of one of these particles. They are all identical. Now, this sum here can be written in another way. Let us define as n sub j as number of particles in energy level EJ. We are considering this energy level diagram. Then we can write the total energy in this manner. Number of particles in with energy E1 times the value of the energy. This one times number of particles that have this energy plus number of particles with energy E2 and this sum continues. Of course, the total number of particles is fixed. It is n, which means the sum of these quantities, number of particles in energy level 1 plus number of particles in energy level 2 must obey this constraint. All right. Now, number of particles in energy level EJ is given another term. It's called occupation number. Occupation number of one particle level EJ. This expression is it may contain infinite number of terms here, but because of this condition, very many of the occupation numbers will be 0. Therefore, when there are just n particles, we are going to have just a few terms, non-zero terms here. Let us consider an example. Five particles. And any selection of N1, N2, N3, and so on, such that when you add them up, you will obtain 5, because total number of particles in this example is 5. Any selection of N1, N2 with this constraint, with such a constraint, is a permitted, possible value for the total energy. Let us say, in our example, N1 is 3 and N3 is 2. Because 3 plus 2 is 5, and we have just 5 particles. Occupation numbers of all the remaining levels must be 0. All other Nj must be 0. So with this example of occupation numbers, what is the total energy? According to this relation, 3 times E1 plus 2 times E3. This energy is one of the possible energies for the total system of 5 particles. There are no restrictions about which N1, N2, N3, N4, and so on you select as non-zero values, as long as the total, when you add them up, must be 5. As a further example, let us assume that we have these 5 particles are independently moving in a one-dimensional box with box size A. In that case, because our energy expression all right, Ej, Epps times J square. J is 1, 2. In this expression, our usual symbol is N, remember? Here, but J means the same thing. So I have used J here for the quantum number. Then the lowest energy is just Epps. This is 0 here. The next allowed energy is 4 times Epps. After that, 9 times Epps, and so on. We may show this example on the energy level diagram of a single particle in the following manner. I will indicate, I will use X symbol to mean if an energy level is occupied by a single particle. So in our example, the lowest level has 3 particles. So I will show it by this. First particle, second particle, and the third particle. They are all in energy the lowest energy level. Each X means a different a particle. This level is unoccupied. Our terminology is this. Levels with occupation number 0 are called unoccupied. Therefore, here again, our terminology is a yes or no type terminology. Occupied versus unoccupied. Occupied means occupation number is different from 0. Unoccupied means occupation number is 0. This level is unoccupied, so I go to the next level. This is the third level here. And in our example, it is occupied by 2 particles. So I draw 2 axes to indicate that the occupation number of this level is 2. What about the higher energy levels? All the occupation numbers are 0 there. They are unoccupied. Okay. Now we can write the total energy here more explicitly. The lowest level contains 3 particles, 3 times its energy, Eps, plus the next level doesn't contain any particles. Occupation number is 0. So 0 times something always will give 0. Such 0 results are not written explicitly. We just skip them. The next one is occupied by 2 particles. And what is the energy of each particle? 9 Eps. Now, the remaining levels are unoccupied, and therefore they do not make any contribution. This is where we stop. Now we add 2 times 9 is 18 plus 3, 21. So 21 Fs is one possible total energy for this 5-particle problem, using the particle in a box model for each particle. Now, the particles in chemistry are mostly electrons. The electrons from an atom or in an atom, or electrons in a molecule. Electrons are identical particles. However, there is one constraint when we use electrons as our particles. The constraint is the Pauli exclusion principle. You have heard of Pauli exclusion principle. Now, when the particles in question are electrons, there is a constraint, as I said, which is called Pauli exclusion principle. Must be obeyed. Even when we assume the electrons are non-interacting, they are not repelling each other, all right? Non-interacting electrons. The Pauli exclusion principle must be obeyed. Now, there is a simple statement of Pauli principle in terms of the occupation numbers. And it says maximum occupation number of a 1 electron level is 2 times G. Here I'm considering a little bit more general case where G is the degeneracy of the one electron level. In our example here, if we use the particle in a one-dimensional box model for the electrons, now we are assuming all the particles are electrons here. Then the degeneracy of each level here is 1, which means all of these energy levels are non-degenerate. So here, in this example, so when we apply the Pauli principle to this model, then G is 1, 2 times 1 is 1. Therefore, maximum occupation number of one of these levels is 2. Okay? And what are the other possibilities? If the maximum occupation number is 2, there can be no higher values for the occupation number. 2, 1, 1 is also possible, and also 0. 0 means unoccupied. So, for G equals 1 for all levels, Nj could be maximum is 2, or 1, or 0. Now the general case applies, for example, to more realistic orbitals. You have seen in your general chemistry course for the orbitals in hydrogen atom, for example. There are s orbitals, there are p orbitals, there are d orbitals, and so on. S orbital is non-degenerate, but p orbitals are degenerate because there are, how many p orbitals are there? 3 p orbitals. We usually call them px, py, pz. There are 3 orbitals. And similarly, in d-type orbitals, there are 5 orbitals. They are degenerate. All those all 3 p orbitals have the same energy. All 5 d orbitals have the same energy. They are degenerate. So this expression applies to them also. So what is the maximum occupation number for a p orbital? 2 times 3, 6. Maximum occupation number for a d orbital is 2 times its degeneracy, and for a d orbital it is 5. 2 times 5 is 10. Returning to our 1D box problem, those energies are all non-degenerate. Now, if the particles are electrons, is this selection of occupation numbers allowed? What do you see here? 3. Pauli exclusion principle must be obeyed. We cannot select 3 for any one of the energy levels. Maximum is 2. So, now let us ask the following question. What is the ground energy, the lowest possible energy for these five electrons in this model. To get the lowest energy using this expression, I should start from the lowest value for the energy, for the one particle energy, and then use maximum value for occupation number. But if the particles are electrons, then maximum value for any of these occupation numbers is how many? 2 in this model. Therefore, graphically, we can show it for 5 electrons. We can select, for the lowest one particle, one electron energy, maximum occupation number is 2. Now I have to use the higher one particle level because I have 3 more electrons. Maximum occupation number of this level is also 2. I have so far 4 electrons, but how many electrons do I have? 5 electrons. So the 5th electron in the for the lowest total energy, I have to put here. So this means N1 is 2, N2 is also 2, N3 is 1, and all the remaining occupation numbers are 0. Remember, this is for the lowest possible energy for the total system. So in other words, it's the ground state energy which we are using here. Also note that this total energy, 21 EPS, is not allowed because of the Pauli principle. When we are considering electrons as our independent particles. Such an energy would have been possible if the particles were not electrons. For example, if the particles were helium atoms, 5 helium atoms, all right, then there is no Pauli exclusion principle for helium atoms. When we say helium, you should imagine a helium atom has a +2 charge in the nucleus, and then 2 electrons are moving around it, and overall a helium atom is neutral, no electric charge. So imagine just 1, 2, 3, 4, 5 helium atoms. Then we may, for some purpose, we may use this model, particle moving in a one-dimensional box, to describe the motion of 5 independent helium atoms. In that case, because there is no Pauli exclusion principle operating, such an energy is allowed. However, if our particles are electrons, then this energy is not allowed. So the lowest possible energy is 2 times EPS number of particles times the energy plus number of particles times this, 2 times 4 eps, plus 1 times 9 eps, so this is 8, plus 9 is 17, plus 2 is 19. So the net result is 19 eps, and this is the lowest possible energy for a system of 5 electrons moving independently in a one-dimensional box. Excited states of the system are obtained from such a diagram by promoting one of the electrons from the ground state, which is described by this diagram, to unoccupied orbitals. The notation or use of symbols in this case, when we consider electrons, is slightly different from the general considerations in the sense that an electron has a property called spin. Experiments show that an electron has just 2 spin states. The spin states are commonly shown by the symbols alpha symbol and beta symbol. So we say the electron has an alpha spin or it has a beta spin. These are using letters. We also use graphics to indicate the spin state. The alpha spin is indicated by an up arrow, and the beta spin is indicated by a down arrow. When we use in energy level diagrams like this, instead of the axis, the arrows are used mostly when we are dealing with electrons. So I will draw the same diagram. Eps, 4 eps, 9 eps. Let's indicate one more, 16 eps. So the ground level, ground state for 5 electrons. Maximum occupation number is 2, but this diagram is showing that the 2 electrons cannot have the same spin. They have to have opposite spins. Also here, you may put either a alpha spin or a beta spin here. Doesn't matter because they will have the same energy, all right? So this is how we show using the spin symbols, the arrows here. Now, this is the ground, all right? Excited states for the system are obtained starting with the ground state configuration, which is this one, and then promoting one of the electrons from occupied levels to unoccupied levels. For one possibility would be excite this electron to that level, not touching the. So this describes one possible excited state for the 5 electrons. What is the energy, total energy here? 2 times Fs plus 8 Fs, 2 times 4 Fs, plus 16 Fs. This will give 10 plus 16, 26 Fs. So this diagram is showing you one possibility for the excited state, which is near to the ground level. Of course, it is not necessary to excite the highest. It is not necessary to excite the electron from the highest occupied level to get excited states. You can excite one of these electrons to either here, because this is partially occupied, all right, or to that one, or some other level. All of these are possible, and they are allowed by Pauli exclusion principle. For example, if we had excited from this level to that level, what would have happened? Let's show them here, here, this. So excitation is from here, and we excite one of the electrons to the nearest one, like this. Now, what would be the total energy? 2 times Fs, this one, plus 4 Fs, plus 2 times 9, 18 Fs. This would give us 24 Fs. Therefore, in this model, this energy, 24 Fs for the total excited state energy, is smaller than 26 Fs. So what do you conclude? This excited energy level is lower than that excited energy level. Please note that excitation from the lowest one particle, one electron level to this level is not allowed, because then occupation number would be 3. But we can excite from this level to this level also. Then you should calculate for that case that the total energy would be 27 Fs. How did I do it? I know the ground total energy. What was it? 19 Fs. When I excite from this level to that level, then 9 minus 1 is 8. So I added 8 to 19, and the result is 27 Fs. Therefore, in this model, what is the first excited state of the total system? It is this one, isn't it? This is the first excited state. The next excited state is that has energy 26 eps, and after that is 27 eps. Please note that in this case, the occupation numbers are 2, 1, 2, and the rest are 0. In this case, occupation numbers are 2, 2, 1 for this level. Now some definitions, very important definitions. I have already mentioned the concept of orbital. In fact, you already know it from your general chemistry course. But here I'm going to give a rigorous definition so that you should memorize the definitions of what's an orbital and what's an orbital energy. Orbital. This term is used only for electrons. An orbital is a, let me write, is a one electron function. Now, so what should you understand completely? It's a function. We are talking about just one electron. Now, what is the maximum number of variables which are required for a single electron? The highest dimensional space that the electron could be moving is three-dimensional space, isn't it? So if the electron is moving in 3 dimensions, how many variables do you need to locate where it is? 3 variables. In that case, this function is going to be a function of 3 variables. But we can impose some constraints to the motion of the electron. For example, we may force the electron to move only on the surface of this table. This is a plane. In this case, how many variables will such an electron need? Just 2 variables, isn't it? Then it is going to be a function of 2 variables. We can proceed further. We can say we force the electron only to move along 1 dimension, as in the particle in a box problem. In that case, the electron is going to have just 1 variable. Therefore, this definition for orbital as a function is quite general. Wherever or whichever model you are using to describe the motion of electrons, this definition is applicable. So, when we use particle in a box model, which means we are forcing this electron to move along a straight line, then the functions psi j 2 over a, this is the normalization factor, it is not important, but this function These are the state functions for a particle moving in a one-dimensional box. And the corresponding energies are F times J square, where J is 1, 2. When we discuss the particle in a box model, we have used the symbol small n, but J means the same thing as n. Don't get confused, okay? I have used J here because in this notation I had labeled the energy levels with EJ and occupation numbers with NJ. So, any one of, if we are using the particle in a box model to describe some properties of the electrons, these functions are the orbitals. All right? Now, the energies, the corresponding energies are called orbital energies. The critical point is that the particles you are considering must be electrons. Only then you use the term orbital and orbital energies. Now the electrons we are considering may come either from an atom, or the electrons could belong to a single atom, or the electrons could be moving in a molecule. In that case, to distinguish the type of electrons, atomic electrons or molecular electrons, we use one more word before this term, orbital. If the electrons are in an atom, we call them atomic orbitals. Short AO. If the electrons we are considering belong to a molecule, then we call the orbitals molecular orbital. Similarly, the orbital energies, if the electrons are in an atom, then we will say atomic orbital energies. And if the electrons belong to a molecule, we will say molecular orbital energies. Before we stop here, once again, orbital energies are numbers, but orbitals themselves are functions. They are not numbers. They are functions. Here is one example. The orbitals that you have seen, you have read in your general chemistry course, s orbitals, p orbitals, d orbitals, right? They are also functions. But they are functions of 3 variables. And of course, what type of orbitals are they? S orbital, p orbitals, d orbitals, atomic or molecular? Atomic orbitals. Okay, take a break.